we've now reached the point where we can begin talking about algorithmic techniques to solve linear programs. And we're going to do that by first talking about a fundamental algorithm for solving linear programs called the simplex method, or the simplex algorithm. Now, this isn't the only way to solve a linear program. There are other algorithms, and in fact, when we finally get to talking about complexity, we'll discover that there are algorithms whose complexity is actually better, at least asymptotically, than the simplex method. There are a lot of reasons why we have to cover the simplex method first. One of them is a lot of these other algorithms are hideously complicated. They require a lot of higher math that some people in this course might not have, but also they may require some intuitive understanding of what an algorithm like the simplex method is really doing. They don't use the same fundamental procedure, but you would benefit from understanding the simplex method first. Another reason is basically no course on linear programming would be complete without talking about the simplex method in a variety of different ways. There are several different variants of it. And then finally, it turns out that the simplex method exposes a lot about what's really going on with linear programs to the extent that we can use the simplex algorithm in proofs. We can actually use as a statement inside of a theoretical proof. We can say, if we apply the simplex algorithm to this, this will happen. And we can actually use that to help prove other things, which is really helpful. We're going to need that later. So here's a linear program. We might remember from the previous lecture that this is in standard form. All of our constraints are less than or equal to. We've got all of our constants on the right-hand side, no constant in the objective function, and I'm working with a maximization problem. And we know that any linear program can be put into standard form. And if I prefer maximization to minimization, any linear program can be reframed as a maximization problem. You might also remember from a different previous lecture that if I take a look at any linear program, the feasible region is a convex polytope. And I've mentioned that there might be some difference of opinion about this. We might use the word polyhedron in some cases. I'm going to just say polytope in any case. I'm going to talk about the feasible region or the polytope corresponding to a linear program. Even if it's empty, even if the linear program is infeasible, I will consider that to have a polytope with no points in it. And it's worth differentiating at this point between what it means for a linear program to be bounded and a polytope to be bounded. So this polytope here is bounded because it doesn't have an infinite volume. It's got a finite volume is being enclosed by the different half spaces that comprise this polytope. If the polytope were unbounded, it would mean the volume is infinite. It would mean that one of these walls was missing and it went off to infinity in some direction. For the linear program to be bounded, it means essentially that if there are any feasible points, there is an optimal solution. In other words, it isn't possible, if this linear program is bounded, it isn't possible to make this objective function, which I'm trying to maximize, arbitrarily large, to make it go to infinity. If the linear program is unbounded, it means it's possible to make that there are feasible points that I can make the objective function as large as I want. So there is no maximum. It's generally, maybe you can establish that if the linear program is unbounded, the polytope has to be as well. But it's not the converse is not necessarily true. There can be linear programs with an unbounded polytope, with a feasible region that has infinite volume, but yet which still do have an optimal solution. And I've got an example of that on the next slide, a two-dimensional case. Here is a minimization problem in 2 dimensions. It has an optimal solution, which is this point here. And it turns out, though, that the feasible region, the polytope, has an infinite area. It goes off to infinity in that direction. And without going into too much detail, the reason why this can happen is if I look at the gradient, I'm minimizing, if I look at the gradient of this, it sort of points sort of like this. And we know that for minimization, we want to walk in the opposite direction of the gradient, which sort of pins us into this corner here. So it doesn't actually make much of a difference that the polytope has an infinite area, because if we're looking for the minimum solution, we are up against a wall at some point, and that means there is a definitive minimum to this linear program. So keep that in mind. A linear program being unbounded is distinct from the feasible region being unbounded. We also talked about this property, that if we are looking at a linear program, we mostly framed it in terms of cases where the feasible region is bounded, but if we're looking at a linear program that has an optimal solution, that optimal solution will occur at some vertex of the polytope. And I know that this is a claim that we were only really able to justify intuitively in the earlier lecture because we didn't have enough tools at our disposal to write a formal proof. We're going to rely on that. That's one of the key criteria for the simplex method to work, is this claim. We actually do have enough tools, now that we know about standard form, we actually do have enough tools to write a proof of this. I would rather wait a bit longer. So I'm sorry if you were a bit frustrated that we didn't see a formal proof of this fact yet. You're going to have to be frustrated for a bit longer because I'm still not going to write one. The reason is because when I do write one, it will be long and complicated. And if I write one now using what we have, it will prove this fact. I mean, we will have a proof of the fact. It won't tell us that much else about the world. It won't really help us with anything besides, I guess, allowing us to rest easy knowing that this claim is actually true. If I wait a bit longer, the proof will be easier because we'll have more tools, and it will make more sense, and it will tell us more. The proof I can write if we wait a bit longer will actually explain a bit more about what's really going on. And the other reason is, of course, because writing proofs on a blackboard in front of a class of people is lots of fun. Writing proofs on a screen for people to watch on a video later is a little bit less fun because there's less of a chance for people to talk about it and ask questions. So as a result, I'd rather conserve the set of proofs that I write on the screen. So I'm going to put this one off a little bit longer. I want to talk a bit about what the simplex method does first. So, what is the simplex method? In this course, I'm going to use the term simplex method and simplex algorithm pretty much interchangeably. I generally like to call it the simplex algorithm when I'm referring to actually applying the process, or for example, writing code for it. When I talk about the simplex method, I'm mostly talking about the core technique that it uses. So what it does is it finds the optimal solution of a linear program by walking around the vertices of the feasible polytope, because we know that one of those vertices will correspond to the optimal solution. We should also observe that we saw in a previous lecture, if we know that the maximum or minimum occurs at a vertex, we could always solve the linear program by just finding every single vertex by brute force and then looking at all of them and just deciding which one has the maximum or minimum solution. We know that there are a finite number of vertices, and therefore this is just a discrete search. I'm just iterating over a set of things. The key thing to observe, though, we also talked about this in a previous lecture, if I have big O(n) constraints or big O(n) variables, the number of vertices could be more than 2 to the n. So that means that obviously it's exponential time, which is not great. But we could argue, hey, if I only have 10 constraints, or 20 constraints or something, then, big O of 2 to the 10 or 2 to the 20 isn't the worst thing in the world. The problem is, in practice, we often work with linear programs that have 100 constraints or 100 variables or 1,000 or 10,000 variables. And that's the issue, is that the brute force approach isn't going to work there. It's not only that it's going to be slow, it's that if really all we can do is iterate over 2 to the 1,000 vertices, we're not going to do that. If we start that now on the fastest computer on Earth, we're not getting that done by the end of this course, or maybe my lifetime. So we need some other option. We need some method that's a little bit more precise than that. Before I continue, I got to talk about this. So this is, I made this slide when I was preparing this lecture originally in March, so a couple of months ago, and I've left it in because I still don't actually have a good answer to it. I know what I've done, but I still don't have a good answer. I know what other people have done too. So it seems like most authors prefer to write the name of the simplex method with all lowercase. The reason it's called the simplex method is that a simplex is a geometric object that I guess historically was seen to have some relevance to what the simplex method does. If you look up the simplex method or the origin of the name, so I think Wikipedia talks about this a bit, it says something like, well, we could interpret what it does at each step as dealing with what is called a simplicial cone, which is relevant to this object called a simplex. But in my mind, what that really means is, by the modern interpretation, we don't consider the simplex algorithm to really work on a simplex. It doesn't really use a simplex. So instead, this is just sort of a name it has, just like my name is Bill or William or whatever. And therefore, I think it should be interpreted as a proper noun, and not just as a method involving a simplex, because we don't really consider it to use a simplex these days. So by contrast, we could consider, you might have learned, well, you should have, because it was a prerequisite to this, you would have learned about the algorithm's merge sort, which is often spelled without capitalization. And that's because this is what it actually does. It sorts by merging. So this is a description of the algorithm, although I should add, frankly, I often capitalize the M in merge sort. you might compare that to this other algorithm called quicksort. So what does quicksort do? Quicksort sorts a list or an array by recursively partitioning it. And therefore, you might observe that this name doesn't really describe what the algorithm does. It doesn't sort by being quick. And of course, the irony, I guess, is that it isn't even that quick. I mean, in practice, it's actually asymptotically slower than a lot of other sorting algorithms. But it doesn't sort by being quick. This is just marketing. This is just a name the inventor came up with for it because it needed a name. And that's why we capitalize it, because it's a proper name. Again, my name is Bill. We capitalize that because it's not a description of me. I am not a Bill. I'm just a person named Bill or William. Again, Bill isn't actually my real name. So by this logic, because the simplex doesn't really factor into this algorithm as much as it used to or people think it does, I think this is just what we call it, as opposed to a description of it. Therefore, I'm going to treat it as a proper noun. So simplex method, capital S, capital M, simplex algorithm, capital A, capital S. I'm in a minority when I do that. Most authors, including the authors of our books, don't do that, but I've tried writing it in lowercase, and it offended my sense of propriety. So in my slides, I'm going to capitalize it. Hold it against me if you will. This is my excuse. So to start the simplex method, we have to find one vertex of our polytope. Because what the simplex method does is it walks around the vertices of the polytope, along the edges. So we have to find a vertex to start with. And I've mentioned a few times in the past that it turns out in a lot of ways the real difficulty of solving linear programs is just finding any feasible point. And this is something I'm not going to address directly today because we have to talk about how the simplex algorithm works before we can solve the bootstrapping problem of how do we find any feasible point to start with. So just to be clear, if we could find any feasible point in the middle of the feasible region, on the side of a face or whatever, it isn't actually that tough to go and find a vertex from there. But we need some vertex of a polytope before we can run the simplex algorithm. So in this example, it turns out the point 0, 0, 0 is a feasible point. What's interesting, one thing you can contemplate, is that if I have an LP in standard form and the point 0, 0, 0 or the all zero vector is feasible, it's guaranteed to be a vertex. So that's something to mull over. There's no guarantee that the point 0, 0, 0 is always going to be feasible, though, but it is in this case. And for now, for this lecture, we're going to talk about LPs where the all zeros vector is a feasible point, because that gives the simplex algorithm something to latch onto, somewhere to start. So that would be this, and the algorithm then walks across edges of the polytope. It walks between vertices, inspecting the solution at each step until it decides that a particular vertex is optimal. So we'll watch as it does that. And it turns out here is the optimal solution. And the optimal objective value happens to be 10 1/4 at 1 1/4, 5, 2. I'm interested looking at this because as we proceed in the course, you will notice that I tend to think that real numbers or decimal expansions are anathema. If you've looked at the assignment, you'll notice that I insist that we use fractions for everything, that we do not use decimal expansions. I'm writing it this way to be magnanimous because we want to phase into that gradually. But we want to work in a mode at this point in the course where we are working with exact rational arithmetic. It turns out these numbers are exact. I mean, these are all rational numbers, but we know that the dangers of using decimal expansions are that if what we're working with aren't powers of 2 or something, we end up with some trouble. We end up with infinite expansions. It turns out that, as I've mentioned, the simplex method or the simplex algorithm isn't just one thing. It is, you could think of the term simplex method as describing the core technique, walking between vertices of the polytope in a certain way, which I'll begin defining in this lecture. There are lots of choices that have to be made along the way. And it turns out that, in a sense, the simplex algorithm is doing a sort of local search. This is the optimal solution over here, but there really isn't any particular heuristic that tells you, hey, if you're standing down here, this is the direction you have to go in to get to the optimal solution. There are ways to know vaguely that you shouldn't go in certain directions, and yes, it might be, maybe this is a good way to go, maybe this is a good way to go, but it turns out there isn't any easy way of knowing exactly where the optimal solution is until you get there. And so the algorithm has a lot of implementation decisions that you can make, including which edges do you walk along and when. Although we'll notice when we finally see it that it doesn't seem at first like that's that's what we're actually doing. It's not obvious that we're walking along edges of a polytope. That's one reason why I felt it was so important to talk about geometry in advance, so that we have that image in the back of our heads. So I'll get back over here. There are lots of ways to implement this. We're going to start with a dictionary-based approach to the simplex method. And we're going to see that even within the dictionary interpretation, there are lots of different choices that have to be made by the implementer. There are lots of different implementation decisions. We'll see later in the course a completely linear algebraic way of interpreting the simplex algorithm. So that is, it interprets it entirely in terms of matrices and the basis of a vector space. And so we can't think of the simplex algorithm as being fully defined. If I talk about merge sort, I am pretty much talking about one algorithm. It's true that there are variations of merge sort for like lists and arrays and things, but pretty much it's always the same algorithm. The same set of things gets done. The simplex algorithm is an entire family of things. It's much more broad. Now, the intuition behind the simplex method, as far as I can tell, so talking to people about this, most people, if you describe, once you demonstrate that the optimal solution happens at a vertex, the idea of starting at one vertex and wandering around the polytope until you get to the optimal solution, that seems to work. I mean, most people seem to agree that makes sense, that is sort of intuitive. On the other hand, there are a lot of choices we have to make along the way, and also there's the question of, wait a minute, like, what is a vertex? How do we find a vertex of a polytope given only a bunch of constraints without having to just enumerate every possible vertex? So there are a lot of conceptual aspects. There's a lot of ground to cover before we can really understand it in terms of wandering around the outside of a polytope. So here are some questions. The first one, the biggest one, frankly, the one that we're going to get to in the next lecture, is how do we find a starting point? If I'm going to wander around between vertices of a polytope, starting at a vertex of the polytope, you need to give me a vertex to start with. How do I do that? It feels almost like circular logic. Like, oh, the optimal solution is easy to find if you start walking on the polytope, but that doesn't give me, any way of finding the polytope. It could be floating anywhere in space. So we'll get to this. And it'll be very interesting once we've seen the basic simplex method, where this isn't so much of a problem. So today's lecture is mostly going to talk about what if we know that the all zero vector is feasible. So we already have this problem solved for us. It's really sort of interesting. It's almost amazing how once we have that basic algorithm down, we can use the simplex method to find ourselves an initial feasible point. Okay, the next one is something called pivot selection, which is if we're standing at a particular place on the polytope and we want to get closer to our solution, where do we go? Do I go up? Do I go over here? Do I go back this way? And strangely, there is no real right answer. There are a lot of conflicting priorities. Obviously, I guess our highest priority is usually, can we get to the optimal solution as quickly as possible? Take the shortest path. And the answer is no, we can't, it turns out. The answer is we do not yet know of any pivot selection rule that guarantees us the shortest path. We at least want to avoid things like walking in circles, which turns out is another separate concern, in fact. It's related to this, but we treat it as a separate concern. We'll get to that, I think, after the first midterm. Then there's this. What happens if we end up at a place on the polytope where we can't make any progress? So what happens if we take a step that doesn't seem to actually move us in any direction? That's called degeneracy, for maybe it's clear why we call it that. What if we end up stuck somewhere? How do we get unstuck? And that, of course, ties into this idea of cycle avoidance. It turns out that degenerate, what we'll call a degenerate dictionary in the simplex method, is a pretty natural occurrence, and it's not a big deal. We just need to have some reassurance that we're not going to end up stuck at one particular place forever. So we're going to begin with this lecture talking about basically none of these problems. We're going to assume that none of these things are ever going to happen, and we're going to talk about if you know that the zero vector is feasible, which means if you start at that point, you're standing on a vertex of the polytope. If you know that, how do you get from there to the optimal solution? That's all we're going to talk about now. The next topic will be, okay, wait a minute, what if the all zero vector isn't feasible? How do I find a vertex of the polytope? And interestingly, the solution is use the simplex method. Just use it a different way. So here is some linear program that in 2 dimensions that has a bounded feasible region. We've written it out in standard form, and I want to talk about the contribution of each constraint to the feasible region. So we know already that each of the sides of this polygon is the boundary of one of those half spaces, because I constructed my feasible region by taking the intersection of a bunch of half spaces. And each half space is defined by a line and all of the points on one side of it. So if my polygon is constructed of a bunch of different line segments, it makes sense that I can't have a single constraint that contributes 2 line segments. So each constraint contributes one, at most, one line segment to the outside of my polygon. And I can map those out. And I've got I've made a bigger version of it on this slide here. So which constraints do we have? We have 5 constraints, 3 linear inequalities, and then, well, these are all x, y greater than 0 is a linear inequality, but they're just the constraints on the optimization variables. So the line segments themselves are places where the constraint is met at equality. So the half space for, let's see, x is greater than or equal to 0. The half space is everything on this side of the line. And that means the line itself will be where that inequality is met at equality. So x equals 0. Similarly, I've got y equals 0 down here. I've got this, a solid line would be the constraint negative 2x plus y minus 1 is equal to 0. And just to be clear, this linear constraint here is equivalent to writing negative 2x plus y minus 1 is less than or equal to 0. I've just moved the 1 over to the left-hand side. So this solid line would be that constraint. This blue line would be this constraint. And then finally over here we have the third constraint. Okay, so each line segment, each bounding segment of my feasible region represents one of the constraints being met at equality. The reason I care about that now, the reason I'm only bringing that up now, is I want to talk about what happens in terms of the values of each constraint at a vertex. We know vertices are important. What's really happening there? So what about this vertex? Okay, this vertex lies on the intersection of this line and this line. And we know that means it lies on both lines, obviously. That means that 2 constraints, this one and this one, are both equal to 0. They're both being met strictly at equality. They're tight bounds at that point. Notice also that none of the other constraints are being met at equality at that point. So the constraint x equals 0, it's way over here. So this point does not meet that constraint at equality. The constraint y equals 0, same story. And then this constraint here is way up here, so this point does not meet this constraint at equality. So notice that at that vertex I chose, 2 constraints are being met at equality. Notice also there are 2 optimization variables. Let's try a different vertex. Well, here we have this one here. That would be this constraint and this constraint. 2 constraints being met at equality. And indeed, still 2 optimization variables. It turns out, in general, we can expect that. If I've got n optimization variables, and I look at any vertex of the polytope, I can expect that that corresponds to the intersection of n constraints. It could be more than n constraints if 2 constraints are happen to coincide. There actually could be cases where multiple constraints all sort of coincide at the same vertex. That's fine. But I can expect in general at any vertex that if I'm working with n dimensions, so n optimization variables, that at any vertex of the polytope, n constraints among the collection that I have will be met at exactly at equality. Maybe more than n, but never less. So that slide said what I just said. I can then convert this linear program in standard form into dictionary notation. I end up with this dictionary. Notice how I've defined 3 slack variables, 1 for each of the 3 constraints. There is no slack variable defined for these constraints here, but there is an understanding that whenever I use dictionary form, whether I write it out or not, that we always have every single variable that I use defined to be non-negative. So in this case, we've got all of these are implicitly expected to be greater than or equal to 0. And I'm noticing a typo here. Sorry about that. Obviously, the variables over here are x and y. I have accidentally used x1 and x2 here because I tried changing formatting at the last minute. Sorry about that. This would be x and this would be y in this case. But it doesn't matter. We're just going to start using a dictionary now. So we've got x1 and x2. Once I change over to have each constraint represented by a slack variable, I now have, I guess, a much more elegant way of viewing this, because now I still have all of these line segments, the same feasible region, but now I have, at each vertex, two of my variables, who cares whether they're the optimization variables x1 and x2, or whether they're w1, w2, w3. At each vertex, two variables will be equal to 0. And that'll just be whichever two correspond to the two line segments that are intersecting at that point. So two of my variables, doesn't matter if they're slack variables or optimization variables, two of them will be equal to 0. That's what it says. And in general, that is true in n dimensions. So if I have a linear program with n optimization variables, x1 through xn, and you might be able to see now why I switched over to saying x1 and x2, and I was sloppy and didn't switch everywhere. If I have n optimization variables, so I'm working in n dimensions, and I've got m constraints, and I put my linear program into dictionary form, so I have my slack variables w1 up to wm. If I look at any particular vertex of the polytope, there will be n of those variables equal to 0. Some collection, some combination of optimization variables and slack variables, at least n of them will be equal to 0. Maybe more, but at least n. And we'll see later that in the event that more than n of them are equal to 0, that is when we have what is called a degenerate case. And we'll get to that, I think, 2 lectures from now. Let's go back to this example from that last lecture at the end of the discussion about standard forms. We talked about systems of equations, and I wanted to make 2 huge points. So one of them was this idea of what's called a pivot operation, which we'll get back to in a minute. But before that, it was a really big deal that I talked about how writing out a system of equations states a set of relationships. Rewriting the system of equations by algebraic manipulation doesn't change anything about the underlying relationships. It doesn't change anything at all. If I interpret it differently, that's my choice, but it doesn't change the relationship. So let's just remind ourselves of that. Here I have y equals 6x plus 10. This is stating a relationship in terms of x and y. It's true that when we write it this way, we make assumptions about what that means. So typically, if I write the equation with y on the left-hand side, y equals, usually when we write things like that, we are trying to communicate that y is a dependent variable, that y depends on x. That's an inference that I'm drawing. That isn't a property of this equation. This equation is stating a relationship that's agnostic as far as independent versus dependent. It's just saying that the two variables are related in this way. And it's worth considering it's an invertible relationship. So this shouldn't be interpreted to prejudice us in favor of assuming that y is dependent. We do that because as a convention, we tend to write it this way if y is the dependent variable. But I could rearrange terms to write it in terms of x. Now, x appears to be the dependent variable. Well, fair enough. How I choose to write something, if I'm writing it in a proof or anywhere else, is a function of what I want to communicate. So it's no different than my choice of words when I write a sentence. It's true that if I choose words in a certain way or I use a certain tone of voice, people infer certain things about what I'm saying. But the words I'm using are communicating some underlying fact which may be the same both ways. Think of that same property as holding here. Just because I wrote the equation a certain way doesn't mean I've changed the relationship that I'm stating, because I could always rearrange the equation back into whatever form I want. And so the key thing is the same relationship is expressed both ways. The only difference is how I choose to interpret things. That's a really big deal. And I feel like if we don't keep that in mind for what we're about to do, things are going to get unpleasant. We really have to understand that the manipulations we're doing are not changing the relationships between variables. They're just letting us look at them in a different way. Okay, so let's go back and take a look at this dictionary representation. I've switched LPs. I'm now working on this LP here. It's still in standard form. I convert it to a dictionary, and it's got 3 optimization variables, x1, x2, x3, and 3 slack variables, w1, w2, w3. And so I've got my dictionary over here, and let's stare at it. So first, I have to define some terms. I don't want to define terms this early, but I've got one term I really need to define right now, which is that we're going to give a special name to the set of things down here, the set of rows below the objective function. As you saw at the end of the previous lecture, we can, and we're going to in a minute, modify the dictionary to change which variables are down here, down at the bottom underneath the objective function. So I need to have a name for that collection of variables. We are going to call this the basis. And you might have heard the word basis in linear algebra, and in a strange way, this is the same thing. This actually is a linear algebraic basis of some kind. We won't see why it's called that until about a month and a half from now. Until we get to the linear algebraic interpretation of the simplex method. So for now, unfortunately, we just have to remember that these variables are together comprise the basis, and that we call them, therefore, basic variables. So I would say W2 is a basic variable, and X3 is a non-basic variable. So the only variables that are called basic variables are the ones that look like this, that are defined with an equal sign in the basis rows. And we can talk about the basis row for W3, the basis row for W1, or whatever. Now back to this example from a minute ago. Notice how when I define an equation like this, I'm implying that y is a dependent variable and x is independent. We can think about basis versus non-basis, or basic variables versus non-basic variables in a similar way. So notice how the non-basic variables all appear in the expressions of the basic variables, but they are sort of the independent variables in those expressions. So, and in general, it's going to be the case that a variable is either non-basic, so it has a column of the dictionary, or it is basic. It'll never be both. So W3 is basic, X3 is non-basic. And I know that because the word basis and basic are being defined sort of out of nowhere here, it can be hard to remember, and I will admit that even for me it was difficult. It wasn't until I actually began preparing this course that I didn't have to keep looking up what basic meant versus non-basic. I actually spent a while with a sort of mnemonic that was, if I keep forgetting when I'm reading a book and it says basic variables, I always think, I had to for a while think, okay, so basic meant the variables that are below. So, B for basic, B for below the objective function. The variables that are below, those are the basic variables. The variables that aren't below, those are non-basic. So I know the term comes out of nowhere. Maybe the mnemonic helps. You'll find once we spend a lot of time talking about this that eventually it's natural, especially once we see the linear algebraic stuff, like why the word basis is actually being used. And so, yeah, the slides are now going to define non-basic variables. So now I want to talk about pivots. So a pivot operation. And I demonstrated a pivot operation in the last video. In the video about standard forms, I talked about a pivot operation without any other context. I just explained it in terms of rearranging a dictionary for no particular reason. So the goal of a pivot operation is to exchange a basic variable for a non-basic one. It is to take a variable that is in the basis and make it a non-basic variable, and then also take a variable that is not in the basis and make it a basic variable. So it's rearranging the equations to make some variables that appear to be dependent appear to be independent, and vice versa. The same way that over here, I can always rearrange an equation like this to make x appear to be the dependent variable. So in a pivot operation, we take something out of the basis and we put something in the basis. We exchange. We define the variable that enters. We define the variable that becomes part of the basis. So it'll be one of these non-basic variables to be called the entering variable. It's going to enter the basis to become part of the basis. And then, I guess conversely, we choose a variable in the basis and we take it out. It leaves the basis. We call it the leaving variable. This terminology isn't helpful. I know this because when I was learning the simplex method originally and relearning it and then relearning it again to teach this course, I kept forgetting what it meant to enter or leave. Because for me, terminology that isn't self-explanatory is always the worst. Trust me on this, there appears to be no better word to describe these things, so we might just have to get used to the terms entering and leaving. The key thing to observe about a pivot operation, just like those equations from earlier, all I'm doing is rewriting the dictionary. I'm rewriting the set of relationships that exists in a way that lets me look at it differently. That's it. It does not change the relationship between variables. I'm going to scroll back to that slide again. In exactly the same way that if I rewrite this equation to make x dependent, I am not changing the relationship. I'm just exposing the relationship in a different way, which might help me understand what's really going on. That's it. I'm not changing it. The reason I keep emphasizing that is I feel like, based on my own experience, that if we don't keep that in mind as an invariant, it's just at the top of our mind as a key fact, it's really easy to lose track of what we're really doing here, why we're doing all this rearrangement. We begin to think that the rearrangement is somehow what's solving the problem, when it isn't. The rearrangement is allowing us to see the solution more easily. Now, fine, fair enough. That's great terminology, and I guess that, more emphasis about that this operation won't change relationships, but what is the operation actually going to do then, Bill? Fine, let's try a pivot operation. I would like x3 to be my entering variable and w2 to be my leaving variable. And the goal here is that when I'm done, x3 will have its own row in my basis, and w2 won't. w2 will have a column. w2 will be a non-basic variable. So how do I do that? Well, the first thing I do is I observe that this row here is going to be gone when I'm done, because I'm going to take w2 out of the basis. What do we know about this row, though? Well, I want to have a row that expresses x3. So I want to be able to write x3 equals something. Well, what I could do is I could just solve this row for x3. So I'm going to do that. I'll do that in long form. So I've got, let's see. So w2 equals 2 minus x2. I'll just rewrite the whole thing. I've only become aware in the last few days how difficult it is for me to draw w's on the screen. I don't think in the previous courses I've taught, I haven't needed to write out w's by hand on the screen. So w2 equals 2 minus x2 minus 2x3. And that tells me if I move x3 over to the left and w2 to the right, 2x3 equals 2 minus x2 minus w2. And if I just want to solve that for x3, then it equals, I'm going to actually divide the whole thing by 2 first. So 2 minus x2 minus w2 all over 2, and then that finally implies, just to try and clean this up, x3 equals 1 minus 1/2 x2 minus 1/2 w2. Notice that I'm using fractions here. That's going to be a big deal on assignments and exams. So I will not accept as an exam or assignment answer, unless I explicitly say that I will not accept an answer that says 0.5 or some decimal expansion. I want a fraction. I want a rational number expressed with integer numerator and denominator. So I get that. Okay, there it is. It's this. I derived it for you. Here's an expression for x3 that I was able to compute by using this leaving variable x2, because I know that when I'm done, w2 won't be in the basis, so why don't I use this row as a way of finding an expression for x3. Okay, so x3 equals this. Okay, great. Okay, now what do I do? Well, what I want to do when I'm done, I want to have a row in my basis for just x3, but I also, for x3 to be a basic variable, it can't appear on the right-hand side of anything. On the other hand, w2 will be a non-basic variable. It'll appear up here, which means w2 is allowed to appear on the right-hand side of other equations. So what I need to do now is I have to find a way of getting rid of x3 from everything else that involves it. So what I could do is I could notice that, wait a minute, x3 just equals this. And notice how this expression doesn't involve x3, obviously. It's x2 and w2. So what I'll do is I'll just say everywhere I see x3, we'll sub in this new expression I've gotten by solving the w2 row for x3. So I do that. I have to do that everywhere that I see x3. So that would be in the objective function and in this row for w3. I've blacked this out because it's irrelevant now. I'm still working on what I'm going to do with that space in my basis. But first, I've got to get rid of x3. What I do is I just sub in that expression I just computed. I just solved one row for x3. So I know x3 equals this. This states x3 in terms of the other variables that I have on hand. And now I just sub that in. So I sub that into the objective function there, so that would be this term here, and I sub it into this thing in the row for w3. And then I collect terms, and I end up with these. In the row for w1, x3 doesn't appear, so I don't do anything. The row for w1 remains unchanged. And now what I do is I take what I have, I set the objective row to be this, I set the w3 row to be this, I leave the w1 row unchanged, and finally, in this position here, in the blacked out row, I sub in that expression for x3. And we'll notice, once we're done collecting like terms, we indeed have a dictionary where x3 is a basic variable, and W2 is non-basic. I eliminated W2 from the basis, but in exchange, because of the way that I solved for x3, W2 did end up getting involved in some of the other equations, in the objective function and in the row for W3. So that's what we expect when, and this is the result of x3 entering the basis and W2 leaving the basis. And so we performed a pivot operation by doing this. Now, again, I'm going to say it one more time. This pivot operation did not change the set of relationships between variables in any way. All it did was rewrite the system so that I can observe the dictionary that I get when I have certain things in a basis. And in a minute, we'll explain why that's so critical, why that really helps us perform the simplex method. Let's try one more. So I've got this dictionary now. I want to perform a pivot with entering variable x2. So x2 is going to enter my basis, and w1 is going to leave my basis. So the first step is I have to take my leaving row and I solve it in terms of my entering variable x2. So let's see, w1 equals 3. So a 3 is a sideways w, so if I can't draw w's, I can't draw 3's. 3 minus 2x1 minus x2. And that's, I guess, an easier one to solve. x2 equals 3 minus 2x1 minus w1. Okay, there we go. That's step 1. Okay, step 2 is I now ignore this basis row that I'm working on, and I then sub in this expression everywhere else that I see x2. So I have to sub this in here and up in the objective function. And so I do that. So I ignore that row that I'm still working on, and then in the objective function and in the x3 and w3 rows, I sub in the expression I just got for x2. And after collecting terms, I end up with this set of rows here, and then I take each of these rows and I replace whatever is currently in the dictionary, I replace it with this. And so I replace this, and I do this. The next slide's going to clean that up a bit, and I end up with this. And then finally, I stick that expression I got for x2, the entering variable, I stick that in the row that gets vacated by the leaving variable. Now, the process of pivoting, just like I said before, doesn't change anything. And you can verify this to yourself, because if you were to do the same operation in reverse, it is a reversible operation. So an example would be what we just did here. We had x3 be the entering variable, w2 be the leaving variable. If I go to what I come up with at the end, whoops, sorry. I guess the last pivot we did was, no, sorry, that was good. If I have this, I can just reverse that. I can have the x2 be the leaving variable, and let's see, w1 be the entering variable. And if I do that, I end up with the same dictionary I started with. You can try that. I'm not sure if that's that good practice. But if I were to just do the same pivot in reverse, starting from what I ended up with, I would end up back where I started. So all I've done is I've rephrased the dictionary in terms of which variables I want to define in terms of which other variables. The reason we care for the simplex algorithm is that if we make certain assumptions about the values of some variables, this representation makes it really easy for us to understand what's happening at a particular vertex of the polytope. I should also point out, if you are looking at this video or these slides after having watch the whole lecture or whatever, or for midterm review or something, you will notice this dictionary would never actually appear in the middle of the simplex algorithm because of this thing. So this is a demonstration of what pivoting does. This is not necessarily a good step for the simplex algorithm. The reason that I did this step is to show that pivoting doesn't depend on the same conditions the simplex algorithm depends on. We can pivot any variable for any other variable as long as the two variables have some relationship in the dictionary. It's also worth, if you're watching this video in like July or something, it's worth considering the dictionary above is not feasible. We'll see what that means in a few minutes. It turns out the dictionary is in fact dual feasible, which is a term we will not see defined for another month or so. Okay, let's talk about the simplex algorithm. And the key here is that the dictionary, this statement of the basic variables being stated in terms of the non-basic ones, the dictionary and pivoting are just a way of representing and writing out relationships. Performing a pivot doesn't change the relationships. On the other hand, just like if I write something like y equals 6x plus 10, maybe that's telling me something. The way I write it is meant to tell the reader something about the way the relationship is applied. We can choose to impose an interpretation on our dictionary. And the key interpretation that we're going to impose is, we might remember, if we have a linear program that has 3 optimization variables and any number of constraints, we have that fact from earlier that says at any vertex of the polytope, 3 of the variables I have, so 3 variables among this collection of 6, will be 0. Guaranteed. Maybe more, but at least 3. So at any vertex of the polytope, 3 variables must equal 0. And basically, the reason we're using a dictionary for the simplex algorithm and pivoting and everything else is maybe we get to decide which 3 variables will be the ones equal to 0. I know that at any vertex of the polytope, 3 variables equal 0. Why don't I decide that those variables must always have a certain status in my dictionary? So sorry, I didn't skip to this slide. Because the LP is in 3 dimensions, it's got 3 optimization variables. Any vertex of the polytope will correspond to a case where 3 variables from among all of the variables I have must equal 0. Now, consider also that the assignment x1, x2, x3 equals all zeros is feasible. The way you can verify that is, you notice if I set x1 to 0 and x2 to 0 and x3 to 0, then all of the constraints, just the left-hand side of every constraint comes out to equal 0, which is less than these numbers. So that means that the point 0, 0, 0 does meet all of the constraints. It is a feasible point. Okay, so that's one observation. It does meet every constraint is being met. Another observation is, if I set x1, x2, and x3 to be 0, well, wait, if they're all zeros, then these all just end up being 0. Okay, and that means that I guess W1 equals 3, W2 equals 4, W3 equals 1, right? Well, yeah, obviously, that's dead easy. If I know that all of these variables are set to 0, and I want to know the value of W2, you just read it right off. Because everything over here are expressions of things that are equal to 0. So if I want to know the value, I just read off the constant column. Well, that's convenient. So how about this? If I know that at any vertex of the polytope, 3 of my variables will always equal 0, let's define the following convention. Let's require that at any given point, whatever 3 variables have to equal 0, those must be the 3 non-basic variables. So if I see x1, x2, and x3 non-basic, I assume those are the variables that are supposed to be equal to 0. So let's take a look at this dictionary, and under that interpretation, try and figure out the value of each variable. Okay, so the non-basic variables are x1, x2, and x3, so they're equal to 0, by our convention that non-basic variables are always set to 0. What's W1? Well, W1 is defined in terms of x1 and x2, but they're both 0 because they're non-basic. So W1 is equal to 3. That was pretty easy. W2 is equal to 4, and W3 is equal to 1. Well, that's nice. Now, it is permissible for one of these things to also equal 0. Remember that it's possible for there to be a vertex where more than 3 variables are 0, but at least 3 variables must equal 0, and we will adopt the convention that if we want to talk about a specific vertex in terms of a dictionary, we will always put these 0 variables, whichever variables happen to equal 0, they will always be put outside of the basis. They will be the non-basic variables. So here is the simplex method. I'm going to start from this initial dictionary where x1, x2, and x3 are equal to 0. And we can observe that the point 0, 0, 0, so x1 equals 0, x2 equals 0, x3 equals 0, this is feasible for this LP. We'll see later that you can tell whether it's feasible by whether all of these numbers are non-negative. If any of these are negative, well, that would violate, so suppose that we had W2 equals negative 4. We know we have the constraint W2 is greater than or equal to 0, so that wouldn't be a feasible point. So I know that at my initial dictionary, I'm looking at a feasible point by my interpretation. If I assume that the non-basic variables are equal to 0, then I've got x1, x2, x3 equals 0, but that's a feasible point because we already verified that for this LP. So the simplex method is starting from a dictionary where you have, which is feasible, that corresponds to a real feasible point in the linear program, perform a set of pivoting operations to increase this number. And the reason we want to increase this number is if we take a look at some dictionary, actually, I guess we can just look at this one. If we take a look at some dictionary and I ask you, if we assume that the non-basic variables are 0, what's the value of W2? Well, the answer is it must be this, because everything else in that row is equal to 0. If we assume that the non-basic variables are 0, what is the value of the objective function? Well, I guess it's the same logic. These are all 0, so the objective function has to just be this. All right. So it sounds like we now know what we want to optimize. If I want to maximize my objective value, what I want to do is wander around between vertices of the polytope with the assumption that at any given vertex, 3 variables will be 0, and I will make sure that at every step, those are going to be the non-basic variables, that they're all set to 0. And as I wander around, this value will change. I'm going to keep wandering as long as I can find a way of increasing this constant. And we'll see when we get to the result, eventually I'll reach a point where I can't increase it further, and then this will be my optimal solution. So there is quite a bit you have to take on blind faith here. I hope that at this point in the video, you at least can believe why using a dictionary representation and setting all of these variables to be 0 can really help, because it can make it much easier to know the values of the other variables. Now, this technique only works if you start from a dictionary that is feasible, if you start from a dictionary that corresponds to a real feasible point. And in this case, we have that, because we know that the point x1 equals 0, x2 equals 0, x3 equals 0 is feasible. So let's try this out. Okay, initial dictionary. The objective value is 0, and the variable assignment is this. And remember, I just set all the non-basic variables to 0, and then I read off the basic variables from the constant column. Question, can I increase the objective function? So remember that the only constraints that exist when I'm working with a dictionary are that every xi has to be non-negative, and every wi has to be non-negative. In dictionary mode, those are the only two sets of constraints I care about. Everything else has been encoded into the dictionary. So the question is there anything I could do that would increase the value of the objective function? Well, I think, I could just increase, 10 times x3. So the objective function is 0 plus 10 times x3, or plus x1, or plus 6 times x2. x3 is currently set to 0 because it's a non-basic variable. We have a convention, all non-basic variables must be 0. On the other hand, if I had the ability to give x3 a larger positive value, then the objective function would have a larger value, right? Because the objective function is 0 plus 10x3. If I set x3 to be equal to 1, then the objective function would have the value 10. So the answer then is yes, I can increase the objective function because there's some variable in the expression for the objective function that if I increase that variable to a positive number, the objective function will increase. Now, to be clear, I could also increase x1 or x2. The reason I've chosen x3 is because this big coefficient seems to me to indicate that I can get more mileage out of increasing x3. If I increase x3 to the value 1, the objective function goes up by 10. If I increase x2 to the value 1, it only goes up by 6. So maybe I get more mileage by increasing x3. Okay, so I think what I could do then is I could find a way of giving x3 or any number a non-zero value. Now I should also think, wait a minute, if I give any of these variables a non-zero value, I have to take them out of I have to put them in the basis, because non-basic variables must be 0. So if I want to increase any of these to a non-zero value, I have to find a way of putting it into the basis and swapping it for something else. So let's choose x3. I'm going to choose x3 as my entering variable. It's going to enter the basis. The reason it has to enter the basis is that I want to give it a non-zero value. And it can't be non-zero unless it's in the basis. So I choose x3 to be my entering variable. Now what I have to do is find a way, find some variable to be my leaving variable. I have to find something to swap with x3. But I have to be mindful that if I do that, that whatever I swap with doesn't violate any constraints on that thing. So obviously I have a constraint, x3 is greater than or equal to 0. But what I want to do is increase x3 to be a positive number. So this constraint's not going to get violated. On the other hand, I might run the risk of due to the other relationships that apply to x3, if I set x3 to the value 100, I might end up in trouble. Let me demonstrate that. So suppose I set x3 to be the value 100. Notice that right now x2 is equal to 0. So that means W2, I'll write it out, sorry, W2 equals 4 minus 2x3. Notice that if I set x3 to be the value 100, then W2 will be 4 minus 200, which is negative 196, which is less than 0. And obviously W2 has a constraint acting on it, so we have this constraint that W2 has to be non-negative, and for the sake of saving some time, so does W3. So I know that if I set x3 to be 100, then W2 will go negative, and then we've got a problem. So we can't let W2 go negative. Okay. Similarly, I can't let W3 go negative. So I say, okay, well, W3 equals, if x2 and x1 are fixed at 0, then W3 equals 1 minus x3. Which means obviously x3 can't be set to 100 because then W3 would be negative 99. So these relationships do imply that x3 can't just be increased to anything. It can only be increased to an extent that doesn't violate the non-negativity constraints on the other variables, W2 and W3. If you're wondering why am I not talking about W1, it's because there isn't any relationship between W1 and x3, so it's irrelevant. So I guess the question is, how much can I increase x3? Well, if I have to keep W2 and W3 to be non-negative, then I guess that means that 2x3, in the case of W2, 2x3 has to be less than or equal to 4. So that implies that 2x3 is less than or equal to 4. Because if 2x3 is bigger than 4, this expression goes negative, and I can't have that. Similarly, this is saying that x3 is less than or equal, x3 is less than or equal to 1. Because if x3 is greater than or equal to 1, this goes negative, and then I've broken this constraint. Okay, so these two things together, I mean, 2x3 this is the same as just saying x3 is less than or equal to 2. Okay, so both of these rows of my dictionary give me constraints on how much I can increase x3. It looks like, though, the tightest constraint is this one. W3, because of the relationship between W3 and x3, x3 can be at most equal to 1. If x3 gets any bigger in the current situation, then W3 goes negative, and I'm not allowed to let any variable go negative. And so the slides are now, I've gotten ahead of the slides a bit. The question is, can I increase x3 to be 17? And the answer is, well, no, because if I do that, if x3 is larger than 1, then W3 goes negative. And if x3 is larger than 2, then W2 goes negative, and I'm not allowed to let any variable go negative. So what I need to do is choose a leaving variable. Ultimately, my goal is to find something to swap with x3 in the basis. And I'm going to use the following rule. I'm going to do what I just did a minute ago, and I'm going to figure out what bound is put on my entering variable by each of the rows of the basis. So for example, W2 is going to force x3 to be less than or equal to 2. W3 is going to force x3 to be less than or equal to 1. So for each row on the basis, I compute the upper bound that that row puts on x3. And it may not always put an upper bound on x3. So for example, in this case, there was no upper bound imposed by W1. But I look at all the rows and I see what upper bound is imposed by each variable. And then I've written that out in better prose here. So W2 imposes the bound x3 is less than or equal to 2. W3 imposes the bound x3 is less than or equal to 1. What I'm going to do is I'm going to choose as my leaving variable whichever row imposes the tightest bound on my entering variable, which in this case is this one. W3 imposes the tightest bound on x3. And so I choose W3 to be my leaving variable. The slides are going to state this in more formal terms because we're actually, if we think about what I was really doing there, the bound is actually imposed by each thing is, if I look at the constant at the beginning of each row and the multiplier on my entering variable x3, the bound that I get will be it'll be m over c, or sorry, c over m. So in this case, that equals 4 over 2 equals 2. And then down here, m is equal to, so on this row, x3 is less than or equal to c over m. Well, c is equal to 1 and the multiplier is equal to 1, so that equals 1 over 1 equals 1. So the slide is giving a more formal way of interpreting this. What it's saying is, because you know everything that you're not currently dealing with, all of your variables that are not your entering variable, they're all going to be set to 0 in all of this, then you can compute the bound by just looking at the constant column and looking at what the multiplier on your entering variable is. And you then choose as your leaving variable the row that gives you the tightest or the smallest upper bound. And so in this case, it happens to be W3. Now, it could be that there's a tie. There could be multiple rows that all give you the same tight upper bound. Then you just have to choose one of them. We'll come back in a later lecture to what rules we should employ to decide which one to choose. But for now, if there's a tie, just choose whichever one you want. So I choose x3 is my entering variable, and I've decided that w3 is my leaving variable. So we chose our entering variable because we perceived that increasing x3 would increase our objective function. We choose our leaving variable based on the entering variable. We use the entering variable to determine our choice of leaving variable. All right, now I perform a pivot operation. And I guess it might be a good idea to map that out. So I'll run through the pivot operation on this slide here. Okay, so my entering variable is x3 and my leaving variable is w3. So I'm going to begin by writing out this row, the row of my leaving variable, in terms of my entering variable. That's going to be pretty easy because there's no multiplier. So x3 equals 1 minus x1, and then I move w3 to the right-hand side, minus w3. Okay, so I'm just going to clear that right out so I don't get confused. Okay, so that's going to be the basis row for x3. The next thing I have to do is to delete x3 from everywhere else that it shows up. So I have to sub in, everywhere I see x3, I sub in this expression. Okay, so I have now, instead of 10 times x3, I've got 10 times 1 minus x1 minus w3. And instead of 2x3, I've got 2 times 1 minus x1 minus w3. All right, and then I'll just expand that out in place. So that's 10 minus 10x1 minus 10w3. And then this is equal to 2 minus 2x1 minus 2w3. Okay, and now I just have to distribute terms. So this 10, I'll just fold that into this constant, becomes 10. Now I've got plus x1 and minus 10x1, so I now have minus 9x1, and then I've got minus 10w3. So w3 is my leaving variable. It's going to get its own column, its own non-basic column. I guess I'll put it here. So there's minus 10 w3. All right. And then I do the same thing on the row for w2. So I'm going to subtract off 2. I guess I'll write this. Let me just clean this up a bit. So what I'm doing here is I'm subtracting off this expression. 2 minus 2x1 minus 2w3. Okay, so I've got 4 minus 2 is 2. I've got... Currently, x1 isn't involved at all, but then I subtract negative 2x1, so that's plus 2x1. And then I subtract negative 2x3, which is going to be plus, or 2w3, which is plus 2w3. All right, so I've butchered it a bit, but what I should end up with is zeta equals 10 minus 9x1 plus 6x2 minus 10w3. w1 is the same. w2 is 2 plus 2x1 minus x2 plus 2w3, and then x3 equals 1 minus x1 minus w3. Let's hope I lucked out here. I mean, it looks much neater on this slide, but it also looks like it all matches up. So I perform that pivot operation. Notice that the pivot is actually not really the operative part of each step of the simplex method. Mostly it's finding that entering variable and finding that leaving variable. And then I rearrange my dictionary to reflect my choices. When I'm done, x3 is part of the basis and w3 is not. And notice that because I've changed my basis, I now have a different assignment of variables. So what's the value of x1? x1 is non-basic, it's 0. What's the value of x2? x2 is non-basic, it's 0. What's the value of x3? x3 is in the basis, but because we know that non-basic variables are always 0, we can just read off its value, and it's 1. And then w1 is equal to 3, w2 is equal to 2, and finally, what is my objective value? Well, it looks like right now, It's 10. Because all three of these variables are 0, so my objective function now equals 10. And it did increase. So although this dictionary is stating the same set of relationships I was stating earlier, because of the convention I've adopted where the non-basic variables are always equal to 0, I now, if I interpret it that way, the objective function value is now equal to 10. All right, so then the question is, am I done? Can I increase the objective function further? So what I've done as of the end of this slide is one complete iteration of the simplex method. So the question is, do I need another? Can I increase the objective function further? And the answer is, I think, still yes. So, okay, for this to increase the objective function, I would have to make x1 negative, but I can't. I'm not allowed to do that. x1 has to be positive or 0. So I can't do anything to this term to increase the objective function. Same here. I can't make w3 negative, so it can't help. But wait, if I set x2 to be, I don't know, 1 or something, so if x2 equals 1, the objective function goes up by 6. So, and you might see the pattern here, as long as there's a plus sign in the expansion of the objective function, I might be able to make more progress. So here I think if I increase x2, I might be able to increase the objective function. So I say, well, in that case, let's do another iteration. x2 is my entering variable. Okay, so now I choose my leaving variable. So what I want to do to choose my leaving variable is figure out which of the rows that involves x2, which are only w1 and w2 here, which of these rows impose the tightest bound on x2, on my entering variable. Okay, so the row for w1 is telling me w1 is equal to 3 minus x2, which implies that x2 is less than or equal to 3. Okay, w2 is telling me that w2 equals 2 minus x2, which is saying that x2 is less than or equal to 2. All right, well, that means it's pretty clear to me that the row for w2 imposes a tighter bound. So we'll skip over here. The row for w2 imposes a tighter bound, and that means that w2 is my leaving variable. So I'm going to perform a pivot with x2 entering the basis and w2 leaving the basis. I'm not going to belabor the algebra of the pivot step. I hope that that's somewhat clear by now. I will talk about that in a live lecture where the stakes are frankly a great deal higher to get the algebra correct. So I perform that pivot and I end up with this. And now again, I have a new dictionary, and by my convention that all of these variables are equal to 0, the objective function now equals 22. I've increased it further. And I should ask, what are the values of each variable at this vertex of the polytope? And one of the ways I know I'm at a vertex of the polytope is that if I assume these three variables are 0, then I have met the criteria to be at a vertex of the polytope, which is that 3 of the variables are 0. So x1 is a non-basic variable, it's 0. x2 is basic, so its value is 2. x3 is basic, and its value is 1. w1 is equal to 1, and then w2 and w3 are each equal to 0 because they are non-basic variables. And the objective function is now 22. So that's one more iteration out of the way. I'm going to call back to the beginning of the previous iteration. Notice how at the beginning of the previous iteration, x1 was not a candidate for an entering variable. I couldn't have increased x1 to increase the objective function at the previous step. But now after this iteration, so I get here, and I ask the question again, can I increase the objective function further? And the answer is yes, I can. I could increase x1, which now for some reason is a candidate for the entering variable, or I could increase w3. That's fine. It turns out that either would actually work. In this case, I'm going to use the same logic I used earlier, which is it seems to me like I'll get more mileage out of increasing x1 because x1 has a larger coefficient. If I increase x1 to equal 1, I increase the objective function by 3. If I increase w3 to equal 1, I only increase the objective function by 2. So I'll choose x1 to be my entering variable. And it's interesting to note, in hindsight being 2020, that actually this logic that I'm using isn't necessarily always correct. If I had chosen w3, strangely, this would be the last iteration. I would actually be done. But the logic I'm using doesn't necessarily know what's going to happen in the future. And it does make sense. The largest coefficient is a pretty good heuristic. It does seem like I'll get more mileage out of increasing x1. So I choose x1 as my entering variable. And then I choose a leaving variable. So we have to observe that unlike in the previous two iterations, there is this situation happening here, where the coefficient on x1 in one of the basis rows is positive. So let's just go through the ratio that I get in each case. So if x1 is my entering variable, then w1, with all other variables held at 0, w1 equals 1 minus 4x1. Which implies that 4x1 is less than or equal to 1, which implies that x1, I'm going to write that up here, x1 is less than or equal to 1 over 4. Okay, so what's happening in this row here? Well, in this row I'm saying 2 plus 2x1, so x2 equals 2 plus 2x1. Is there any value I could give x1 that would be problematic? So remember that the reason we're computing these ratios, so the ratio I got here, x1 is less than or equal to 1/4. That's because if x1 was set to anything larger, so for example, if I set x1 to be the value 2, then 1 minus 4x1 would be 1 minus 8, which is negative 7. And then w1 would be negative. And I'm not allowed to make w1 negative. The reason I'm computing these ratios is to make sure that I don't make any of these variables go negative. So what about 2 plus 2x1? So x2 equals 2 plus 2x1. Is there any positive value of x1 that I can assign that would result in x2 going negative? And this is where in an in-person lecture I would wait for somebody to tell me, but I don't know if that's going to work right now. The answer is no. No matter how big I make x1, x2 is not in jeopardy. Because of this plus sign, there's nothing I can do to x1 that would make x2 go negative, unless obviously I made x1 go negative, which I'm not allowed to do. So what that means is that x2 is not going to be our leaving variable. It will never be a candidate to be the leaving variable, because there is nothing I can do to x1 that would damage x2, that would break that constraint. So I just ignore it. So then, among the other two variables, I go compute my ratios. For w1, we end up with the constraint x1 is less than 1 over 4. For x3, we end up with x1 is less than or equal to 1. And that means that my leaving variable is the one with the tightest bound, which in this case is w1. Okay, so I choose w1 to be the leaving variable, and then I perform a pivot, and I end up with this. This, you, I hope, can see the pivot you had to do there was probably a little bit unpleasant, because it involved this ratio 1 over 4, and so you end up with a whole bunch of fractions. 1 over 2, we end up with our objective value being the sort of unsettling 91 over 4. Unfortunately, for better or for worse, you're going to have to get used to doing this kind of arithmetic. We need to have exact rational solutions. It is not sufficient to be writing out real expansions of things, although in this case it would mostly be 0.5s and 0.25s. So then I say I've done the pivot. The first question is, what are the values of each variable? So I notice that w1 is equal to 0, w2 is equal to 0, w3 is equal to 0. x1, x2, and x3 have these values. There we go. I just read them off the dictionary. And then finally, the objective function is this. So just in case we really need a decimal expansion, it's 22.75. And in our previous example, it was 22. So that's an improvement. It's a small improvement, but it's an improvement. Okay, next question. Can I improve the objective value further? And the answer is yes, I can. If I increase the value of w3, I will be increasing the objective function. Okay, so that means w3 is my entering variable. I still have options, and so I still take them. So w3 is my entering variable, and now I go looking for a leaving variable. So here I'm saying that x1 equals 1/4 minus 1/2 w3. And actually, this is worth giving some attention to. So let's do this. So let's see, x1 equals 1/4 minus 1/2 w3, which means that 1/2 w3 has to be less than or equal to 1 over 4. And that means that if I multiply both sides by 2, that means that I end up with w3 is less than or equal to 2 over 4, which is 1/2. So see, I know fractions aren't your favorite, but it is doable. Okay, and then here similarly I've got 3 over 4 minus 1/2 w3, whoops. And then that implies that 1/2 W3 is, I'm going to have to practice my W's between videos, is less than or equal to 3 over 4. If I multiply both sides by 2, then I end up with 6 over 4, which I guess for the sake of simplifying things is 3 over 2. Okay, so I've got two bounds that are formed, and just like before, because I have a plus sign here, there's nothing I can do with W3 that's going to cause X2 any trouble. So X2 has been pretty easy going today. So I don't need to worry at all about computing a ratio for this. Okay, so I compute the ratios for x1 and x3, and I determine, as I did on the previous slide, oh, that typesetting looks pretty disgusting. As I did in the previous slide, the tightest bound is imposed by the row for x1, so it's the bound W3 is less than or equal to 1/2, and that means that x1 gets to be my leaving variable. So I choose x1 to be my leaving variable, I choose W3 to be my entering variable, and then I perform the pivot. And unfortunately for us, doing that pivot does sort of thin out all of those ugly fractions a bit. And now I read off my variables. So I say, well, okay, x1 is equal to, x1 is a non-basic variable, it is equal to 0. x2 is equal to 3. x3 is equal to 1/2. And then let's see, W1 is non-basic, it's 0, and W2 is also non-basic, so it's also 0. And I guess I need W3, don't I? W3 is equal to 1/2. And my objective value is now 23. And then just as with any other iteration, the next question is, can I increase my objective value further? And in this case, we might notice that the answer is actually no. Because everything has a negative sign in front of it, there is no variable that I could increase to be a non-zero value that would improve my objective value. Because I know that every variable has to be positive or 0, the only values besides 0 I can give these three variables are positive numbers, and if I do that, if I make any variable positive, like 1 or 5 or something, it will decrease the objective function because I'm subtracting it away. And it turns out that means that I'm done. I can't increase any variable to increase the objective function. And because this is the objective function, remember that this is an equivalent expression of my objective function. This expression, the equation 23 minus W1 minus 5W2 minus X1, that is equally valid to the expression at the very beginning for the objective function. If I notice that there is literally no way to make this any larger without leaving all of my variables at 0, then I'm done. This is the best objective value I can get, and further, this is this assignment of variables that gives me that objective value. Now, normally when we talk about the solution to a linear program, we usually only care about the values of the three optimization variables, x1, x2, x3, but we have the values of the other three in case we care. So if I want to know what the optimal value of this LP is, the objective value is 23, which is attained at x1 equals 0, x2 equals 3, and x3 equals 1/2. So we're done. We have solved the linear program. We've found the optimal solution. And we can verify that. If I take that solution I just read off, so x1 equals 0, x2 equals 3, and x3 equals 1/2, and I try actually plugging that in, then I will in fact get the number 23. So x1 times 0, x1 equals 0, so that's just 0. X2 is 3, so 3 times 6 is 18. And then 10 times 1/2 would be 5, which does equal 23. So I have my optimal solution. So here are the basic steps. Hopefully you were able to sort of interpolate this from the steps that I went through. The basic steps of the algorithm are find a feasible dictionary. So what does it mean for a dictionary to be feasible? It means that the non-negativity constraints of every variable are obeyed. I'm going to skip way back and we'll talk about that initial dictionary. Okay, I guess this is as good a slide as any. Here is the dictionary that I get by just rewriting the standard form LP as a dictionary. If I now read off my variables in the usual way, x1 is 0, x2 is 0, x3 is 0, W1, W2, W3, they are all positive numbers. All of the constraints are obeyed. Every variable is non-negative. That is what it means for a dictionary to be feasible. If one of the variables was negative, we would not be able to apply the simplex algorithm because it wouldn't be possible to select a leaving variable anymore. Here's an example. As I mentioned earlier, this dictionary is not feasible because at no point in the simplex algorithm should you ever have this. You should never have a variable assigned a negative value because obviously that wouldn't make any sense. So we would never be able to start from a dictionary that looks like this. Okay, so we'll skip back to the end. So the algorithm starts by constructing an initial feasible dictionary. And the problem is, what if, for whatever reason, the dictionary that we come up with initially, like the basic conversion of the LP to dictionary form, what if that's not feasible? And the answer is, watch the next lecture. So we come up with a feasible dictionary somehow, and then we iterate through, and we keep going as long as there are any positive coefficients in the objective row of the dictionary. So we saw... if we look back here, we chose to continue at this step because in the objective row, there was a positive coefficient. We keep going as long as there's at least one of those. So we keep going as long as it happens. We choose an entering variable from among whichever variables have positive coefficients in the objective function, keeping in mind that there could be multiple possibilities, and which one is the best choice is actually a pretty hard question to answer. But the general logic we'll use for now is we'll choose the one with the largest coefficient. Once we've chosen our entering variable, we choose a leaving variable. And we don't have as much choice there. We have to choose a leaving variable that gives us the smallest upper bound on our entering variable. And then we perform a pivot operation. And we inspect the resulting dictionary. If the objective function still has positive coefficients, we go around again. Otherwise, we read off our optimal solution directly from the final dictionary. And I hope you could appreciate how easy that was. It's this. I just pull a number right out of the dictionary. And if I want the values of variables, I can pull those out too, and then assign all my non-basic variables the value 0. So, as I've mentioned, in the example we went through, the point, the all zero vector, was a feasible point. So my initial dictionary, and your initial dictionaries typically look like this. You've got all of your W's are in the basis by default. So there's WM. And then all of your X's are up here. They're non-basic by default, which of course means that your initial dictionary corresponds to the all zero point. It turns out in the previous examples, as I mentioned, that was a feasible point. They were chosen deliberately to make that feasible. What happens if our initial point isn't feasible? What does that look like and how do we fix it? So we'll talk about that in the next lecture. When I'm choosing my entering variable, there could be different options. We're going to call the process of selecting a particular entering variable a pivot selection rule. And those are a big deal. We're probably going to have 2 entire lectures talking about the consequences of different pivot selection rules. The pivot selection rule actually also covers how we choose a leaving variable if there's a tie. In general, if I'm choosing a leaving variable, the only options are the ones that impose the tightest upper bound on my entering variable. But there could be multiple possibilities, in which case my pivot selection rule will have to help with that as well. So that also covers the choice of leaving variable, and then I perform a pivot operation. Now, there's also one other option that I haven't talked about today, which is what happens if we have a linear program that's unbounded? There will be a point in the simplex algorithm where you notice that it's possible to increase your entering variable as much as you want. In other words, you can make the objective function go to infinity. That's actually pretty easy to notice. We'll talk about that in a future lecture. I think that's in the next lecture. So here is the linear program that I gave a while ago, an hour ago, I guess, to illustrate the geometry of the simplex algorithm. Now that we know what the simplex algorithm does, maybe we can appreciate that we'd probably rather not have to solve this one by hand, although it would be good practice. Let's take a look at what that looks like geometrically. We saw as we went through the previous example that we can keep reading off the variable assignment at each step. So why don't we try and visualize that on a diagram of our feasible region? Okay, so here it is. So we'll start at point 0, 0, 0 of our feasible polytope. And we know that x, y, and z are all non-basic, so they're all equal to 0. And we perform one iteration of the algorithm. So we perform one pivot. And it turns out that, well, maybe it's obvious, but we would have chosen at our first step z to be the entering variable because it has the largest coefficient. And so we expect that when we're done, z will have increased in value. And of course, here's the z-axis, and if it increases in value, we should expect to maybe hit that corner there. And we do. Once the pivot is done, if we read off our position, we are at x, y, z equals 0, 0, 1. So we take a look. Do we have a choice of an entering variable? Well, we could choose either x or y. I guess we'll just choose x because it comes first. So I pivot with x entering And what was the leaving variable? I guess W4 was our leaving variable there. And of course, if I look at that and I say, I know that x is going to be my entering variable, I expect x will increase from 0. I should expect x will have a larger value when I'm done. It'll be positive. Okay, so I do that, and then here's the x-axis here, and notice how the point I end up at now increases the value of x. It also increased the value of z, as it turns out, but z was in the basis, and so its value will keep changing as I keep going. Okay, so now I'm at the point 2 over 3, 0, 5 over 3. And I look at my objective function and I say, well, I still have an option. I could increase the value of y. It has the largest, well, actually the only positive coefficient. So I pivot with y entering my basis. So I expect to see a non-zero value for y after the next pivot. And there it is. I actually end up here, where it now actually all of x, y, and z are basic variables. They all have a non-zero value. And I look at my objective function, but it still has a positive coefficient. So I pivot with W3 entering the basis. And I end up over here, x, y, z equals 2, 2, 2. I look at my objective function, and yep, there it is, still a positive coefficient, so I pivot again with W4 entering. We can see we're getting some pretty nasty looking fractions of 11 there. That's not fun. And then I end up here. I have x, y, and z are all in the basis. They all have non-zero values, 5 over 4, 5, and 2. And if I look at my objective function, it's now 41 over 4, but there are no positive coefficients. And so I have now reached the optimal solution. It is this vertex here. Now, as we watch the visualization, if we go back to the beginning and start over, I'm following a path through vertices of my polytope that gets rather efficiently, if I may say so, it does get to this optimal solution. I think there might be a way with fewer steps, but not that many fewer. Okay, so I took 1, 2, 3, 4, 5 steps. If I walked along the bottom, I could do 1, 2, 3, 4 steps. There is a path that would get me there quicker, but that was still a pretty fast route, especially given the other choices. If I chose badly, I could end up going up here and then sort of circling around for a while. That is possible. And it turns out that the choice of path, exactly where I end up going, is a function of the pivot selection rule. And so if I go back to, let's try and find a place where I had 2 choices. So here, at this step, I could have had either x or y be the entering variable. And what that would have meant, I think, is that I could have chosen this variable, this vertex to be the next place I visit, or this one. There were 2 possible choices, both of which would have improved the objective value. And I chose x, which meant I ended up taking this path. But it was because of the pivot selection rule. It was because I guess we used the rule of largest coefficient, and to break a tie, choose the first one. We'll see in later lectures that in many cases, because the pivot selection rule is making a local decision, it's just saying from here what appears to be the best option, it doesn't mean it will actually always take the best path. It's basically making a heuristic choice. And there really isn't a pivot selection rule that guarantees you the best possible decision at each step, although there are some that are pretty good. And so what we have to talk about now that we understand the basic idea of the simplex algorithm, is how do we employ it for linear programs that aren't initially feasible? How do we detect whether it's unbounded? And what are the consequences of our choice of pivot selection rule? Another problem we obviously have to consider, a much more applied one, is now that you've seen me go through one example of the simplex algorithm, how do you get good enough at it to be confident on assignments and exams? And the answer is come to the live lecture. I will also post a bunch of other fully worked examples on slides that show at each step how I choose the entering variable, how I choose the leaving one, that you can also try and go through and then check your work. Because I know that, yes, there is a lot of algebra to do here. We have to do it because it's one of the main outcomes of the course, but we'll only have to spend a few weeks on having to do this low-level stuff before we can begin talking about applications of this, as opposed to having to do, huge numbers of pivots by hand.